So now we will see that P plus n square A by V square V minus NB equal to nRT. We'll again come back to the van der Waals equation. We can write that as for 1 mole gas, let's say for 1 mole gas we can write P plus A by V square into V minus B equal to RT. So we can write that P equal to RT by V minus B minus A by V square. This is the equation we get basically. Now simultaneously we can say that PV equal to RTV by V minus B minus A by V. So obviously you can write PV equal to RT V minus B by V means 1 minus B by V, 1 minus B by V minus A by V, or we can write that PV equal to RT into 1 minus B by V to the power minus 1 minus basically A by V. So this is the expression we are landing up with. And also parallelly you can see the Camerling-On's equation, basically PV equal to RT into 1 plus B by V plus C by V square, like this. So this is the Camerling-On's equation. Now we can derive what is the real coefficient V and what is the constant for the van der Waals equation. So in that case we can write that by expansion you can write 1 R by RT into 1 plus B by V plus B square by V square, like this. This is expansion minus A by V. So obviously if I take RT, we can say 1 plus basically B minus A by RT into V into 1 by V, and we can neglect higher terms because B square by V square, B small v is very high, so in that case it can be neglected. So therefore we can get this expression. So we get PV equal to RT. So with this expression, basically equation 1 and equation 2, if we say compare, then obviously it is basically RT into 1, RT into B minus A by RT into 1 by V, also by RT into B by V. So therefore comparing equation 1 and equation 2, we can get that B equal to basically B minus A by RT. So whatever the Camerling-On's, this is the Camerling-On's equation, Camerling-On's equation is basically Camerling-On's equation, and in that case Camerling-On's equations B and van der Waals equations B minus A by RT, they are basically same quantity, B minus A by RT. Now for the ideal gas, we know that it should be a PV equal to RT. This should follow the PV equal to RT equation. So therefore if it is PV equal to RT, so this term should be 0 to find out the boil temperature, because PV equal to RT do not have any B term. So therefore we can say B minus A by RT should be equal to 0, and it is called boil temperature. So therefore we can write TB equal to basically A by RB. So this is called boil temperature, because in the Boyle's expression or the ideal gas equation, PV should be equal to RT. So there should not be any this term from the van der Waals equation. So B minus A by RT we can say should be equal to 0. So this is called TB equal to A by RB equal to called Boyle's temperature. And also we can say that basically del P, P tends to 0 is equal to basically the del P, P tends to 0 should be the condition for boil temperature, and the Boyle's temperature is basically the TB equal to RB. Now we can prove that how the gas should behave ideally from the van der Waals equation, what condition they should behave, like this. Just for example, over here we have got that gases should behave ideally, gases should behave ideally at very high temperature and very low pressure, that we can prove with the help of the expression over here, equation 1. For example, if we say PV equal to basically RT into basically it is a 1 plus, we can say B minus A by RT, B minus A by RT, let's over here, and 1 by V, we know pressure is inversely proportional to volume, so you can write K into P, like this. So quite naturally, if V tends to 0 over here in the right hand side and T tends to infinity, then PV becomes equal to RT. So therefore, with the help of this expression, that we can say that P tends to 0 and T tends to infinity, the gas should behave ideally, because this term should vanish basically. So P tends to basically 0. So in that case, this becomes 0, and but still there becomes, and T tends to also has to be infinity, because if it is not T tends to infinity, then it will be remaining. So therefore B minus A by RT into Kp should be like this, that P tends to 0. So obviously T tends to, and also T tends to infinity, we can get PV equal to RT. So therefore it is true that gases should behave ideally at very high temperature and very low pressure. With the help of the van der Waals equation, we can prove it. So we have seen that van der Waals equation. Once again I am writing P plus n square A by V square into V minus NV, that is equal to nRT. Again I am writing the van der Waals equation. If we talk about for n equal to 1, again we can write P plus A by V square into V minus V is equal to RT. Now there is a concept of the reduced condition, that is we can write P in terms of pi Pc, that is in terms of critical constant, P equal to pi Pc, and V equal to 5 Vc, and T equal to theta Tc. That means theta times of the critical temperature if we take. So then we can get a reduced expression like P equal to pi Pc plus A by V square into, we can write A by V square into, it is 5 Vc minus B is equal to R theta Tc. If you put all the values like Pc, Vc and Tc, we get basically pi plus 3 by 5 square. So pi Pc, 5 Vc, 5 Vc square, 5 Vc square, 5 Vc minus B, then pi plus 3 by 5 square, theta minus phi, 3 phi minus theta is equal to basically, so you can say if we put the Pc is equal to A by 27 B square and Vc is equal to 3B and Tc is equal to 8A by 27 RB, 3 phi minus 1 into 8 theta, 3 phi minus 1. This is the expression we get after taking all the terms, like we can say Pc is equal to basically A by 27 B square and Vc is equal to 3B and Tc is equal to as well 8A by 27 RB. If we put all the values over here in this expression, so we get pi plus 3 by 5 square into 3 phi minus 1 into 8 theta. This is called reduced equation of state. So that means what? If we know pi and phi, then obviously theta will be automatically determined. So if we know theta, then theta into Tc should be the temperature of the gas, or we can say Tc will be T by theta. Now last but not the least is that Z, called compressibility factor. And this is very important, compressibility, how compressible the gas is. For example, if you look at the diagram once again over here, that we can see that at every pressure over here, this is basically, it is PV observed, this part is PV observed, this is the PV ideal. So over here, this part, let's say it is, let's say X, so you can say PV observed by PV ideal, how much it is, this is basically X by nRT, you can say. So obviously what, then that is called basically Z. So that means if the Z is very low, that means if this P observed is PV observed is this much and PV ideal is this much, so obviously what, PV observed by PV ideal, it is PV observed by PV ideal, obviously Z becomes very low, so easily compressible. So Z should be very low for the compressibility factor. So as a compressibility factor, which makes the basically gas more compressible. So what is Z? Z equal to basically PV observed by PV ideal. Also we can say that is equal to V observed, or you can see V molar volume that is observed by, you can say that is V molar volume, that is, or you can say V bar, that is a theoretical basically. This ratio also can be treated as Z, compressibility factor, and we can say that PV observed also can be written as divided by PV ideal is nRT. So that means what, Z is low. Z, when Z can be low, that means little pressure will decrease the volume much. So in that case Z is low, so obviously A should be very high. So if he is very high, Z will be low, so it will be more compressible, gas will be more compressible. So with this with this compressibility factor, we can say that ammonia should be much more compressible than oxygen, or oxygen may be much more compressible than hydrogen. So that is why the Z basically occurs, Z basically takes into action. So we should consider Z is the compressibility factor, more the intermolecular attraction, maybe the hydrogen bonding with divertible attraction. So Z will be very, very low, and Z low means more compressible. So that way the gas can easily be liquefied. With this, I am concluding the gaseous state, especially the second part of these real gases. And with this, I am concluding, and I want your questions on as queries, and you can connect me in Skype. At the end of this chapter, you will get several questions which we have to solve. And once you are stuck up, you can ask me over Skype in my given account. Be very much scrupulous while you are doing this particular chapter gaseous state, because I have got the relation with the thermodynamics too. Thank you very much.